A small dam on an agricultural property has a length of 20 metres and a uniform cross-section shown below where x and y are in metres. The base of the dam is flat for x between 0 and 5, and we can see that here on the diagram. And the right side is given by y equals x minus 5 squared divided by 4, and that applies for x between 5 and 11.325, which is this part here. The shaded region on the graph below represents the cross-section of a volume of water in the dam with a water level of h. Using calculus, show that the volume of water in the dam is given by V of h is 100h plus 80 over 3, h to the power 3 over 2. Now, I'm going to work out the cross-section area, and I'm going to do that by first of all looking at this rectangle and then taking away the area just here. So that area is going to be, so we need to know the x value just here. So let's work that out by using h is equal to x minus 5 squared over 4, so just from here. And then 4h is equal to x minus 5 squared. So 2 root h is x minus 5. So x would be 5 plus 2 root h. So my area then is going to be h times 5 plus 2 root h. And then we need to take away that area, which will be the integral from 5 to 5 plus 2 root h of the x minus 5 squared divided by 4. So that's going to give me 5h plus 2h to the 3 over 2. Take away, now I've already done this on the calculator. So you can see at the very top of the screen up here, we've done that integral and it gave us this big long expression here. But fortunately with a simplify, that big long expression simplified to 2y to the 3 over 2 divided by 3. So that gives us 5h plus 6h to the 3 over 2 over 3, take away 2y to the 3 over 2 over 3, which is 5h plus 4y to the 3 over 2 over 3. The volume then, that's where we use the length of 20, is just 20 times that. And you'll see that that comes out to be 100h plus 80y, sorry, it'll be h, won't it, not y. I had h on the calculator. So let's just go back and just correct that. And so that would be 80h to the 3 over 2 over 3 as required. Okay, so let's move on to the next part. Use the increments formula to estimate the change in water volume if the water level rises from 6 to 6.1. Okay, so we have dv dh. So we wanted delta V over delta H, and we know that those are approximate. And so the change in volume is going to be dV dH, approximately equal to anyway, times delta H. So if we do dV dH, it is equal to 100. Add 3 over 2 times 80 over 3h to the half. 3's will cancel, so that is 100 plus 40 root h. And so our change in volume is going to be 100 plus 40 root h evaluated where h is equal to 6, and then times by the increment there, which is 0.1. And I think I did this earlier on the calculator as well when I was just preparing for this. And indeed, there it is, 19.80 we'll call that. So we'll call that 19.80 cubic meters. And suppose the water volume at the start of winter is 1,000 cubic meters. On the basis of rainfall data from previous years, the volume of water that will flow into the dam over winter is normally distributed with a mean of 600 and a standard deviation of 200. Assuming there are no other sources of water and no losses, determine the probability the dam will reach full capacity, i.e. a depth of 10, during winter. Okay, so we're looking at 10, but we've got our volume here. So the volume of 10 is going to be 100 times 10 plus 80 over 3 times 10 to the 3 over 2. And calculating that gives us 1843.27. But remember, there was already 1,000 in there. It said start was 1,000, so we're after the amount of water that flows in, which was called VB in the question. VB just there. So VB would be greater than or equal to V10 take away 1,000, which is going to be 843.27. And we're told VB is normally distributed with mean 600, standard deviation 200, and we're just after the probability that VB is greater than or equal to 843.27, and I believe I calculated that earlier as well. So it's just an interactive distribution, continuous, normal CDF. That was CDF, not PDF, but anyway, normal CDF. You can see I put in 843.27 to infinity with a standard deviation of 200, mean of 600, and we get 0.1119.